We have so far dealt with acceleration and velocity at any point during the motion of a projectile. And now it's time to look at displacement as a vector at any point during the motion. So just like we integrated acceleration to get velocity, we are now going to integrate velocity to get displacement. And it's common to use S for displacement. So if we take the integral of the velocity vector with respect to time, well, what we are integrating is v cos theta I, okay, where v is that initial speed, and then in our j component we have minus gt, so g for gravity, plus v sine theta. Since v cos theta is just some constant, this part, when we integrate it, just becomes v cos theta times t, or commonly written as vt cos theta. So that's the horizontal part. And then for the vertical part, well, we have t here. So what happens when we integrate t? We raise the power, so t squared, over the power. So keeping in mind that we still have this negative g, we get negative g t squared over 2. And then for the second part, v sine theta, in the same kind of manner as what we just did before, v sine theta is a constant, so we add in the t, commonly written as vt sine theta. And that's all times j. Now, just to make sure that we know there's a difference between constants as we go. So previously we used the constant c. Here we're going to use the constant d. We want to work out what this constant is. So what do we know about the displacement of the projectile? Well, it could actually be anywhere, I suppose, initially, but we've so far been focusing on the projectile starting at the origin. If this is the case, then we can write that when t is equal to 0, displacement as a vector is equal to 0I plus 0j. That's the origin, right? And so if we were to substitute in 0 and 0I plus 0j back into this line up here, well, we have 0 on the left, 0 here, 0 here, and so therefore that leads us to see that the d that we have here, this vector, what we've been kind of referring to as our constant of integration previously, is just equal to a 0 vector. And so that means we have our equation of motion for displacement. S is equal to vt cos theta I plus negative gt squared on 2 plus vt sine theta j. Now is probably a good time to just take stock of what we've learnt so far and just break it down into the horizontal and vertical components of motion. And a table is a really good way to organize this information. So if we first start by considering the horizontal column, we know that acceleration is 0. There is no horizontal acceleration to consider. When we then think about velocity, that remains constant throughout the entire flight, and that is just the initial speed times cos theta. So v cos theta I is our horizontal velocity. Displacement does of course change, okay, but it changes at a constant rate. So it's vt cos theta. Right, just the velocity that we're moving in a horizontal direction multiplied by the time. So the horizontal components of motion are pretty straightforward. Vertical is that touch bit more complicated because we start with an acceleration due to gravity, negative g j. When we go to velocity, which we integrated, we get minus gt plus the initial velocity component, v sine theta. And so all of that, this is in the y direction. Finally, what we just did, when we integrate again and we go to displacement, we get negative gt squared on 2 plus vt sine theta. So having an understanding of this table is really helpful. It just breaks everything up nicely and gives us a good idea of what's happening for either horizontal or vertical acceleration, velocity, or displacement. Now it's worth noting once again that these are not things to purely memorize, but rather understand how to come up with them. And in the case of displacement, we saw that our sort of constant of integration, which is a vector, but our constant of integration was 0. But that was only because we started at the origin. We assumed that our projectile started at the origin, and that's not always the case. So it's important, especially when we're deriving displacement, that we're careful of that we actually substitute in the correct initial information. In the next video, we will have a go at our second example.